Well, welcome back, everyone. I have a screenshot this time since I had to unshare the screen to reshare, get the recording going. But today will be our last lecture for the entire semester. So congratulations on getting through a 4-credit math class. Meeting for 70 minutes 3 times a week is a lot of work, but we're nearly there. So far on the final exam review, we're on problem number 8. We're probably on track for completing this 100% by the end of the time today. But as usual, if you have any other questions that might come up that you want to take a look at to start us out today or at any point, feel free to interject. Also, this is our last quiz, 13, that's due today. But for any of the work, whether there's any quiz that's gone past due when you check your grade book, any section in my lab that's gone past due, you can still work those sections for full credit on the last cutoff date of May 7th, on Thursday next week. There's also the extra credit for the course evaluation that I mentioned. So once you've done that course evaluation, that pop up when you join our Canvas course, just send me a quick email or message in Canvas, extra credit, dropping your lowest 2 assignments in my lab. Also, there's a major extra credit opportunity for the final exam that we mentioned. The final exam is required, but what it does is if the final exam grade is larger than the smaller grade between these three, it can replace that minimum grade. So far. Okay, and I guess the last standard set of announcements or reminders are, if you haven't scheduled your exam now yet, please do so as soon as possible. Also, for this exam, it's different than exams 1 through 3. It'll be 2 pages of notes that are allowed on this exam. The scientific calculator is absolutely required, and be sure to take a look into this as you're studying for the notes that are provided on the real exam. But that's pretty much reiterating what we've said before. What we'll do now is go back to this problem that we left off on. And we ended class, I think, 4 or 5 minutes early last time, just because this is one that deserves our careful attention. This problem was on exam 3. This problem is one of the problems that we started off the chapter 5, statistical reasoning, on. And you should expect something like this, just a different context, but same style of question on the final exam as well. It's tricky. First thing we want to do is read through the context, and even after you answer the question in its entirety, it's a good idea to read through the context again to make sure we nailed every bit. But maybe before we even get started, one of the things that was really tricky was the words parameter and statistic. Whenever we're saying what the parameter is or the statistic is in context of the problem, we're always going to start off for these questions by saying the average, and then say something beyond that, and same average. And after we do parts A and B, read through the whole context even before that, we'll be able to replace the ... with the specific statement. But don't forget these parts. These were the parts that were easy to miss on our 3rd exam. Okay, to start it out, here's what it's saying here. To investigate the effectiveness of a newly developed organic fertilizer on crop yield, so an agricultural scientist selected a random sample of 350 Roma tomato plants from a large commercial farming operation containing over 50,000 such plants. Well, it's going to ask us to describe the sample, so these are words we want to key in on when it says random sample of Roma tomato plants. Let's highlight that to just keep that thought in our mind. We're told next, at the end of the harvesting season, the scientists recorded the total weight of tomatoes produced by each plant in the sample, measured in kilograms, to evaluate the fertilizer's impact on productivity. So that's the whole experiment, the whole well, not exactly an experiment. This was a study, an observational study. This is the whole description of the study altogether. We need to describe both the population, sample using context. And here's the dichotomy that we mentioned before. When it's talking about the population, The population parameter is going to come back in part C. So what we say in part C loops back in again. Excuse me, what we say in part A loops back in again on part C. Likewise, when we describe the sample, whatever we say in part B, we'll reuse again when we describe the sample statistic. So even if we get something a little bit wrong about anything in part A and B, we could lose some points there. But if you're consistent in parts C and D, you won't be double docked on points in that way. So that gets us started. And these are tricky problems like we mentioned before. So that's why we're taking some extra attention and careful time with this one. Any volunteers for saying what the population might be? Yeah, absolutely, Echo. Echo says all the tomato plants. So we can say here, the population is going to be all Roma tomato plants. And I like that you said plants as well, because it wasn't about the individual tomato. The study is about the plants specifically. We should also go a little bit further. It's not necessarily all tomato plants ever, but it was all tomato plants relative to the commercial farming operation. So I'll say just briefly, all Roma tomato plants grown the farming operation. We're thinking something pretty large scale. The 50,000 is really just here for context. We're not actually going to use that number. And once you have the population down, you know, we're almost done with the parameter. It's the average of something of all Roma tomato plants grown on the farming operation. So let's leave a blank right here. This is the next thing that we're going to have to come back to. But to just really nail down the thought that once you have the population, you're nailing down the parameter, let's say it here. Say it again here, it's going to be average of something. We'll come back to that. And we'll say for all Roma tomato plants grown on the farming operation. So those two to go together, we still need to fill out this last part. But let's turn to the sample next and get this portion in. Sometimes the sample is a little bit easier. So if you solve part B first, that's not a bad strategy either, because the sample comes from the population. And the problem often says what the sample is right here. The sample, we can say, is the 350 Roma tomato plants you could say randomly selected if you liked, or just say, you know, that would be a pretty complete statement. But let's say, to emphasize, it's the ones that they chose, the 350 Roma tomato plants randomly selected. And you can go even longer on this. You could say randomly selected from the farming operation. But the reason you can cut this a little bit short is it's automatically implying the sample came from the population in the very first place. So if you left it off right here, that would still be a complete statement. But let's be specific and say the 350 Roma tomato plants randomly selected from the farming operation. So if you solved part B first, you probably would want to write this whole statement. And the only difference now between the sample and the population is the population is talking about all Roma tomato plants. So that's the emphasis that says it's the population. It's everybody, well, where a person is a tomato plant. So once we have that down, just like we did on part C, there's a blank here we need to fill in still, but the sample statistic is just the average of the sample. So we can say it's the average of something for all 350 Roma tomato plants randomly selected from the farming operation. Okay, so we're nearly done. Now we need to go back to the parameter, part C, part D, which means it's a good time to just reread the context again. What did they do in this observational study? It said at the end of the harvesting season, the scientists recorded the total weight of tomatoes produced by each plant to evaluate the fertilizer's impact on overall productivity. Let's highlight maybe right up to here. So when we do a statistical study like this, very typically we're looking into maybe the statistic is a proportion, some kind of percentage, or it could be the median, the 50th percentile. But for the problems that we did in class, so the one you can expect on the final exam, just like on exam 3, we're looking into a statistical study about averages. So if they were talking about the total weight of tomatoes, the parameter is the average weight of the tomatoes, average produced by each plant. Let's say average weight of tomatoes. And I kind of painted myself into a corner here. Let me say it this way: average weight of tomatoes produced by each plant. Sorry for kind of squeezing that in. For all Roma tomato plants produced by the farming operation. So this is the unknown value. It's the average of something specifically. Weight of tomatoes would have been okay to paraphrase, but I just wanted to emphasize weight of tomatoes produced by each plant. And then once you have that down, it's the same exact thing here. They are actually measuring the average weight of tomatoes produced by each plant. That copies down in both statements for both parameter and the statistic. So this was, again, the trickiest part about the exam 3 question that was parallel to this one. The parameter isn't talking about the weights themselves. It's always talking about the average weight for this kind of problem with quantitative data. You have to say the weight of what specifically? Weight of tomatoes would have been okay, but we put an extra line for specificity. If it's the parameter, you just say what the population was again. If it's the statistic, you just say what the sample was once again. So that's the full rep of those 4 moving parts in any statistical study. Again, it's a tricky question. These change context from context, but the structure of how we put this all down is always going to be the same. Any last questions or comments at all, folks? Getting through question 8. Okay, again, today's review is all about giving hints, advice for studying. This was one question that came up on exam 3 that, in my opinion, was the trickiest one in the entire set. So take another look at your exam 3. If the comments don't quite make sense, don't hesitate to ask me about it by email, message in Canvas. I'll be happy to help. Take another look at this problem. You can find a blank version by going up to the top of Canvas, and the final exam we're going over is inside that folder there. And that'll give you some really good practice. Also, you can practice the one that we did in lecture notes, which is found all the way down here in version 1 and version 2. You can get 2 more problems along those lines. one that we did, and a whole new version in version 2. So this was the chapter 5, unit A problem. But now let's go off to the next thing that we're doing in chapter 5. We did a whole lot of stuff, but again, the final exam can't get too long. The document we're looking at is about the real length of the actual final exam. So aside from population, sample, parameter, and statistic, you could expect a problem along these lines, interpreting a graph, and another problem like this, interpreting a different graph along these lines. So a couple of graph type problems will round up the entirety of chapter 5. Looks like 3 questions total is what you can expect. And not too bad. I think people did pretty well when you analyze the scatter plot information on the exam 3. On our exam 3, it was, I believe, if I recall correctly, a strong linear relationship that was negative. This one, I would say more appropriate to say moderate. If you said weak, that'd be appropriate as well. But it would be a positive relationship because now the trend is upwards rather than downwards. But as usual, let's read through the context, see what's going on to help us answer part B. It says, a botanist is studying growth patterns of a specific fern species in a dense forest understory. So under the canopy of the forest, the researcher wants to investigate if the amount of light reaching the forest floor has a relationship with the size of the ferns. And probably, but here's what they did to really verify that. They aren't just looking for what the relationship is. They want to know how strong it is, what the nature is of the relationship. And so they ran another observational study. They measured the average daily photosynthetically active radiation. So botany is kind of a wild science, it turns out. Organic chemistry, all that stuff. They work pretty hard. All this is trying to say is amount of usable sunshine that actually made it to the plant. Physically active radiation, abbreviated to PAR, that's worth highlighting. That's a quantitative variable, so it has a unit. It's in micromoles, where moles are the same things that we're looking into on the last unit of notes, a very large number. Micromoles per meter square per second. So they're looking at the number of photons that hits the leaf of the plant, so they need area, so meter squared, over amount of time, so per second. And so this whole thing is just saying how much sunlight that's usable by the plant actually hit the plant per area per time. So complicated unit, and that's what this is. Think of this as just the amount of usable sunshine hitting the plant as a rate in that complicated unit. They did this at 100 different random locations, so they worked pretty hard on this. There's about 100 points here. Some of them might overlap directly, so if you count 97, that would be Y. Next, they select one mature fern at each of those locations and measured the total leaf surface area in centimeters squared. So they went to 100 different locations in this forest. Hopefully no one got lost. Then at each location, they usable light is hitting the forest floor. Then they selected one plant at each of the 100 locations and measured total leaf surface area for that one plant, which means they probably disrupted that plant quite a lot, possibly killed it to get an accurate computation. That's the cost of science sometimes. And this is the data that they produced. Context sometimes has been straightforward, sometimes it's been more complicated, but that's been one of the skills that we've been working through pretty much all along this semester. Any questions about the context at the moment? Okay, well, like we mentioned before, just by visually inspecting the scatter plot that we see, the direction we can say is positive. It's an upward trend, so we'll say the direction is positive. And take a look at the other scatter plots that we analyzed, other scatter plots in the other sample exams. Usually we set a strong relationship when the points are very close to a line that goes through this linear trend. Here, there's a pretty good amount of scatter. We've seen worse. We've seen relationships which we've called weak, barely anything going on. We've seen relationships where we said no relationship whatsoever, which means there wasn't even a direction. That's where it looked like white noise. For this one, I think the best answer would be with moderate, so in the middle of the road, straight. If you said weak strength, I'd say that's pretty appropriate as well, but I would exclude saying strong strength. That's where we might lose a point for this particular relationship. So instead using the context, so I forgot that whole part. Let me try to revise. The direction is positive with moderate strength. Let me see if I can backtrack here. It's always good to pay attention to this part right here, which means you have to say something about the study whenever it says using the context. So let's say instead, the daily par, and I'll say instead of total leaf surface area, I'll just say briefly, leaf surface area, follow a moderate, strong, positive. You could say correlation, but we could also just say relationship as well. So there's my revision. Don't forget with context, we have to mention aspects of the study. But it's not so bad because you can just cite the horizontal variable, the vertical variable for each of these axes, and that would do the job for the context. So that's part A finished. Part B is asking us to say a little bit more, but pretty much we're what do you mean by positive relationship when we go to answer part B? Any questions to this stage of the analysis? Okay, let's move on to the next step. It says, what conclusion can be drawn from the scatter plot? Here, we're just going to cite these variables. We can abbreviate them as appropriate and say something along these lines. Usually we're reading the graphs going left to right. We typically mention the horizontal variable first, so it might flow along these lines. Anything you say that conveys the information correctly is going to be fine as well. So if you read right to left and you use this variable first and that variable, but you set it in the right order, that would be okay too. So the way I'll say this is as the average daily par amount of usable sunlight is hitting the plant increases, we're saying increases here because it was a positive relationship. The total leaf surface area tends to increase as well. That's for highlighting, this is the better one to say increases. I need to recall we said we're reading left to right. So we're usually saying increases if we're reading in that direction. The positive relationship was more about the second variable, total leaf surface area. It's going up as we read the graph left to right. So that's the better one to highlight, carry between the positive direction and the statement of the second variable is increasing. So that's our wrap up on that one. On the exam 3, there was a follow-up question about cause and effect. I didn't ask that question again on the final exam, so it's going to be a little bit shorter on this one. That if we were thinking along the lines of, say, cause and effect, I would say, yeah, the more sunlight does cause the plants to grow more leaves. So there is a cause and effect relationship. The reason it's not super strong is that there's more factors involved. Amount of moisture, the amount of available nutrients to the plant, outside competition, causing that plant to either flourish or be diminished. So that's just one factor for how well it's going to thrive. But any last questions or comments at all, folks, getting through this one? Okay, we're nearly through chapter 5. And again, on this problem, everyone did analyzing the scatter plot. So that was kind of a funner section, I'd say. On the next graph, we're going to take a look into, we've done a graph like this before. And if I recall right, this was kind of one of the more challenging kind of graphs that we looked at when we did this in the lecture notes. This didn't make it onto exam 3, but as a hint for the final exam, you should expect something along these lines, but in a different context. So these are some real accurate data for Bonneville County. It says the accompanying graph shows the annual percentage change. Here's where a red flag should start to be indicated. This is percent change. This is not the value of home prices whatsoever. Annual percent change in the average sale price of a family homes in Bonneville County, Idaho from the years 2008 to 2024, which has been a crazy adventure in the housing market. So percent change from previous year, a red flag that this graph is maybe a little bit more trickier than normal. So we need to be really careful with this one. So it'd be good to review what we did in the lecture notes, go back to version 1, version 2 for further problems along these lines in our chapter 5. Now, what's tricky here is all of these values that we see, these are nothing but percents. They're percent changes from the previous year. Years are going in this direction. And I printed the numbers on top of each one of them so we can see the values a little bit more clearly. And part A is kind of like the warm-up equation. It says, based on the graph, in which specific year was the percent change in home prices the greatest? That's a nice question for this kind of graph, because if it says percent change, we're talking about the right one. This is a percent change axis. So all we're looking into is the highest bar in the chart, year 2021. So that's all we have to put down. Year 2021. It has the highest bar. And so that's when the home prices had the greatest percent change. Well, that's one down. They get trickier from here. So again, we're going to analyze the next ones really carefully. Any questions at the moment? Okay, here's where the first question comes up that is a bona fide tricky question. Not that it's meant to be a gotcha question, it's just a tough graph. We can infer this information, but we have to be careful in how we do it. In which year was the actual average home price the highest? The sale price, really, when we say that, a little bit paraphrased here. Any volunteers for when the average home price was the highest on this graph? Yeah, good call, folks. It was year 2022. And it's tricky, right? That takes a little bit of explanation. And in fact, we're being asked to do so based on the graph. So let's look at it in a couple ways. I'll say year 2021. And even though this isn't the explanation, it's a way to kind of get an intuitive feel. Excuse me, 2022, like you all said, I grabbed the wrong year. 2022 is the right year on that one. 2021 is meant to be the thing that's easy to mistake with. It has the highest bar, but not the answer to that question. So one way to think about this is we don't actually know the home sale prices. I'll just say briefly, average prices like it's saying here. They're completely unknown. We just know how much they're changing from a previous year. So let's just make a hypothetical. Let's suppose that in year 2021, some single home price sold for $200,000. Then this bar is saying the percent change in 2022 is it's up. It's up by 14%. That means the home value increased by that amount. So go times 1 plus 0.142 as a decimal. If the average home prices in 2021 was 200,000, then in 2022, up by 14.2% as a decimal means do this. The new value is $228,400. So because it was positive here, it just went up again. Not as much. That was a gigantic increase. That was where the housing market in Idaho Falls, I believe Pocatello was similar, just went completely crazy. Then it towed down, and people who flipped houses and were trying to make a buck started to panic a little bit, and so did the real estate agents. It got even more toned down in, say, 2026, where a lot of agents haven't even made a single sale so far. But now for our overall explanation, we can say year 2022, this is because we do have some negative rates, but that was only 3 years. And these values are higher than all of the negative rates altogether. So we can make a brief statement. This is because from years 2011 to 2022, the percent change is always positive. And so the home prices are always rising. If they're always rising from 2011 to 2022, absolutely exceeding the values in these 3 negative years, that means just the last year in this data set is the maximal year. So let's say it briefly. This means the last year has the highest price. Again, it's a tricky question because the graph itself is just tricky when we're talking about percent change rather than absolute change. The actual absolute values are just completely missing here. Well, that's 2 down. Any questions or comments at the moment? Okay, and thinking intuitively like we've done before, we need to explain in our own words what happened to the actual home prices in 2008 through 2010. This is when the economy kind of went upside down. Some people call this the housing crisis that started in the year 2008. Massive amounts of defaults on variable rate home mortgages. Some people call this the global financial crisis, usually in year 2009. And these days in 2026, this is sometimes being referred to as the Great Recession, where things went really, really bad for the housing market. If we thought about this intuitively, like we did before, through some fast computations, we might make an assumption along the lines that maybe in the year 2007, average home prices were about $100,000. I don't know how accurate that is, but it's in the right ballpark. That would mean in the year 2008, it changed like this. We took 1 minus negative 4.5 as a decimal, 0.045. It went to that value. It dropped to about 95,500. Then it dropped by even more. We multiply again by 1 minus the rate, 0.062, dropping down to below $90,000. Here's where the turnaround is starting to happen, but it's dropping again still, 1 minus 0.021. Now it's at about $87,000. So if our assumption is the average in 2007 is even 100,000, negative rates mean home prices just keep on dropping at each particular year. Then it turns around, actually goes up on this year, and then it starts to become kind of ridiculous. It skyrockets out of nowhere. This is where our local economy for housing just kind of went crazy. I think it's starting to normalize finally. But to put all that into words, what we can say here is the home prices all began, I think all is a weird word there. Let's just say the home prices began to fall in 2008 through 2010, since the percent change is negative in these years. So that's a way to answer that kind of question. Anyone have any other different takes on it or any questions with? Okay, well, there's one more follow-up question on this one.
I'm sorry, I actually did have a question.
Go ahead.
I know you said you weren't looking for to be thorough on the final, but for explain your reasoning questions, what kind of information would you want on there?
Gotcha. So for say, let's do maybe both part B and part C for that question there. So both, and as far as this one goes, in which year was the actual average home price the highest? So to get an explanation down for that one, you would have to say something along the lines of the percent change was always positive in these particular years. So a complete answer, you could paraphrase this down a little bit. As long as you say percent change is always positive, that's the major part of the answer here. That means that the last year has the highest price. I would say that this would be the major thing here. If you said year 22 has the highest price, that's your answer. And this is because from 2011 to 2022, percent change is always positive. That would be a full justification on that one. Does that make sense for that question there?
Yeah, thank you.
You bet. And then along similar lines, part C was, and explain your answer on this one. Explain what happened to the actual home prices in 2008 to 2010. Really, we just had to say they're falling. So as long as we have that down, we're on the right track. And the explanation is they're falling since percent change is negative. And those are the major things to connect together for a complete explanation. So if you made a really short statement and you just said prices are dropping because a percent change is negative, this is the major thing to focus on, and we're just in those target years, then that would be the complete explanation for this one as well. But other questions or comments so far? Thanks for asking about that. Okay, I think through parts A, B, and C, these are pretty much the main concepts about what's going on with a graph like this one. Looking at percent change is kind of like looking at, say, the inflationary pressure, but specifically to average home sale prices, specific to Bonneville County. So it's not like, say, looking into overall inflation as the federal government would state it, but it's along very similar lines. And part D does feel kind of redundant, but let's do it anyways, just for the sake of extra practice concepts. Part D says Consider the period strictly between 2011, 2022. So we are in this region of the graph. This is all we care about so far. The vertical axis here still matters as well. Even though some bars are noticeably shorter, say 2011 was close to 0, some bars are noticeably shorter than others during this time frame. The actual home prices continue to rise every single year. Explain why this is true based on the data shown. And that kind of addresses what we were saying before on the last problem. The reason the prices are always positive is, we could say briefly, this is because the percent change is always positive. So always rising is because we have always a positive percent change. Some years it rose by a lot, like 2021. Some years, not as much, 2011 through 2014. But that's pretty much the takeaway on this one. Again, kind of similar to what we were saying in the prior problems, but just another look at that same concept. Well, we did it, folks. That's the conclusion of getting through this graph here. Any last questions or thoughts or comments at the moment? Okay, well, this concludes our run through on what we're going to see in chapter 5 for the final exam. Again, we did a whole bunch of stuff in chapter 5. I think that was one of the longer chapters for our entire course, but the final exam can't be extremely long. It can't be all of chapter 5. So I try to balance out all the different chapters so nothing gets emphasized more than any other chapter. Likewise, chapter 8, it can't be overly emphasized either. We did spend a good decent amount of time in chapter 8. But for the time we have, there's two questions that you can expect. What I mean is for the time that we're allowed for a final exam, I can't do everything on chapter 8. So these are the two that we're going to focus on. We'll look at them one at a time. And just to reiterate one more comment about a hint for an extra credit question on the final exam itself. Like we said before, expect something along the lines of one question from 8C. It's not for credit on the final exam. There'll be one question from there for extra credit. It'll be the last question on the exam. They'll say it's for extra credit. Your final exam score can't exceed 100%. But if you've practiced these problems, got through the homework, this will be a rewarding section for that reason. So let's look at these one at a time. Before, this is a good opportunity for us to say what formulas are a good idea to include as well, as far as building out your 2-page of notes for the final exam. Chapter 5 didn't have a whole lot of formulas, but you might want to write down some definitions about sample, population, parameter, statistic, just to help out with the first question. For this one, there's definitely formulas, so let's go and immediately grab them before getting into the question. These are going to be formulas from doubling time and half-life. And the way we started off these notes is we were chipping away at the formulas, so they're written one by one. But a great set of formulas is when we got to this table. Yeah, let's take it in this format. I'm not going to ask for the exact doubling time, the exact half-life for this exam. That was more for the sake of us practicing logarithms before we get into the final unit, where we will use a logarithm potentially. We'll have to see about that. Let's see what that question looks like before I make that a completely accurate statement. So here's the formulas we're going to use, the complete roundup. And now here's the context. We're looking at thallium 201. Chemical name is Ti201, or I guess the full name is thallium chloride. It is a special radiopharmaceutical used in nuclear cardiology. So this is some kind of nuclear imaging test. Nuclear because this is radioactive, and the radioactive nature of this is what gives us the image. We're told it is primarily used by diagnosticians for myocardial perfusion imaging to evaluate blood flow to the heart muscle, detect conditions like coronary artery disease or prior myocardial infarction. I'm not sure I'm pronouncing that right. I'm just going to say, or prior heart attacks. So if you have a heart attack, if you're expected to have some kind of coronary blockage, then they inject you with this chemical, and they do a whole lot of other science to determine a nice image of what's going on with your heart to see where damage might be, blockages could occur. And this radioactive tracer, thallium-201, decays at a rate of 0.945% per hour. So in the per hour rate, it looks kind of stable, but again, if this was in per years, it's almost completely just gone. So we have a decay rate that's going to be used for what looks like a half-life, and it does say use the approximate half-life formula. So here's our decay rate. I guess it does say yearly decay as well to help out. So this is a real important medical tracer. First thing we want to find is if you get injected with this, we want to know what is the half-life of that tracer in hours, round to the nearest hundredth. So that means we're going to be using this formula here, the one on the bottom row. Any questions before we throw in the computation? Okay, here's how this one goes. We call this T for time, half for the time for half of the tracer to be gone from the system is going to be equal to, take 70 for our approximate formula. We divide by P, but as the warning in that violet color says, P in this problem is 0.945. We just drop the percent symbol. We don't do anything else with that. 0.945. And this will be in hours. Our value is going to turn into 70 by 0.945. And this is to the nearest hundredth, so 74.07 hours. So it takes a little bit of time, a few days, well, maybe more than a few days. If we divide this whole thing by 24, yeah, about 3 days is what it's going to take for half of this to be gone in your system. So 74.07 hours specifically to the nearest hundredth. So kind of a nastier tracer. This one stays with you for days. Any questions at all, folks, with part A? Okay, now information here is all real and accurate information, and so is part B. So let's imagine something unfortunate happened, and you are in for this kind of radiology procedure. It says a typical adult patient receives a standard initial administered dose of 4.0 millicuries. That's kind of a weird unit, but this is a unit of radioactivity. This is the radioactive dose that you're going to get from this treatment of thallium-201. And that's a pretty large dose, so this is not a procedure they do just out of Sorry, I'm back now. Let me recap what I was saying before. And by the way, I did put in a ticket with the IT department at ISU about what's going on with the Zoom instability. They didn't give me the best answer. There was an update on Zoom, and this problem with Zoom crashing out is Zoom-wide. everybody who used Zoom whatsoever. Zoom had an update and they basically destroyed Zoom, it feels like. It just had a warning on my screen that said my connection is unstable. Hopefully it's stabilizing. Is the video audio coming out okay for folks so far? Okay, I'm gonna try, this seems to happen at the end of class, so something wrong with the program. I think sometimes I call this like a memory leak. Something's been coded wrong. Maybe they've been using AI to make updates, who knows? But yeah, this is a problem that's ISU wide, unfortunately, or anybody who uses Zoom. So I'll just try to be careful on the last part of the notes. If I see an unstable connection, I'll just pause for a moment. And if we crash out like that again, that's pretty annoying, but we'll come right back. In fact, I was in a math department meeting just yesterday, and it happened to our whole meeting too. So I got to see what it looks like from your side as well. Kind of frustrating. Sorry about that, but it's the last day. We'll get through it. So just to recap, this person is receiving a dose of 4.0 millicuries of thallium-201 for their medical imaging. We have a time of 24 hours later, they're done with this procedure. We just want to know how much of the tracer is remaining in their system in terms of their radioactivity measurement. So time from here is going to be 24 hours. And here's all we have to do. We'll follow this formula right here and say, I should recolor code this. That part should be in blue to follow that a little bit more verbatim. We'll say amount of thallium (201) is going to be, take the initial value, the initial dose of radiation in this problem, 4.0 MCI for the abbreviation of millicuries. That's named after pioneers who studied radiation, so that's why it seems like kind of a weird name. And multiply this by 1/2. I recall this being a mistake that I made a couple times in the lecture notes of accidentally putting in a 2. So watch out if it's a half-life problem, definitely put a 1/2 there to be right on track. Then raise it to the exponent of the time, 24 hours, divide by the half-life we did in part A, 74.07. We know that in about 3 days, that's 24 hours times 3, that's a half-life, so it should be 2 millicuries. So this is just 1/3 of that. There should be quite a bit of amount of this remaining. So finally, go back to the calculator, pin 4 times 1/2 to the exponent of 24 over 74.07, and to the nearest hundredth, that would be 3.20. So it hasn't even dropped by 1 millicurie. This person still has a lot of radiation in their body that's being flushed out. 3.19 millicurie. And you know, it sounds scary when you say that in those terms. There's radiation floating around in your body, but this is a life-saving procedure. It's not that bad of an amount. I shouldn't make it sound as scary as it can sometimes seem to be. But any questions at all, folks, getting through this half-life problem here? Okay, well, as far as the real final exam goes, expect one question from that section, 8B, doubling time and half-life, and it's being randomly selected on this one. It's either going to be a half-life problem like this one, or similar doubling time problems that we've seen before. Essentially, the process is about the same, so the formulas go the same. Only difference is the 2 versus 1/2. And the context will direct you on whether you're doing doubling time versus half-life. So that means we're ready for the last question of the day. Let's hope Zoom continues to hold on for us. Here we're going into the final unit that we covered. There were 3 big topics we were looking into. First, magnitudes of earthquakes, then intensity of sound in decibels, and then that hydrogen ion concentration in pH. So 3 logarithmic scales. I did make a hint about the final exam since we were finalizing content just this Monday, which is a short turnaround. The first topic we're really going to be expected to look into for the real final exam is going to be magnitude for earthquakes. So expect and be ready for this formula. This would be a great one to add to your sheet. And, according to what it says right here, I'll keep both because I want the whole definition. But let's keep that idea here. We only did this formula in the lectures, only that formula in my lab exercises. So you can expect the same on the final exam. I'm not going to throw new stuff we haven't studied at you. So here's our last big formula and our last big set of context, pretty similar to the final quiz as well. So quiz number 13 is kind of practice for the final exam. And similarly with all the quizzes, that's why we have all the quizzes in a row. It's not a guarantee, or hang on, I haven't uploaded that yet. But I think I just at least mentioned you should take a look into all of your quizzes. Well, it is actually this one, I just forgot. Version 3 is all of your quizzes in one spot. You should take a look at those. They're not guaranteed to be exam questions, but a lot of them absolutely can be. So here's the context here. We're looking, it looks like, specifically in California. On January 9th, 1857, the Fort Tejon, I guess is how you pronounce it, or Tejon, earthquake struck southern and central California, marking the most powerful seismic event in the state's recorded history. We're told further the tremor was so intense that the Kern River was reported to have flown backwards temporarily. Scary sight. Ground ruptured for approximately 225 miles along the legendary San Andreas Fault. And according to the modern revisions by this geological survey, this earthquake has been refined to, or specified as having, magnitude 7.9. So that's what they define this earthquake as when they say refined to. So that was the worst earthquake in California history, which is kind of interesting because if you look into Alaska, they've had much higher magnitudes in the 9s and so on. The second highest magnitude earthquake in California history is the 1906 San Francisco earthquake. This one struck in April 18th, early in the morning. This one went for 300 miles across the San Andreas Fault. The shaking lasted less than a minute, but the fires caused like almost total destruction, 250,000 people homeless, thousands of deaths. And this one was told to be refined after they study it more and more to a magnitude of 7.8. So we have 2 magnitudes down. And this is a similar kind of question that we did in the lecture, the quiz. We're going to look into the energy released by both of these earthquakes and find out how many times more energy was released in the Fort Tejon earthquake, I'm just guessing on the pronunciation, than in the 1906 San Francisco earthquake. So here's what the process will look like on this one. I'm going to kind of reset my color coding because I think for this problem, it's good to think in terms of what is the first thing we're comparing and what is the second thing we're comparing. So we'll do a fast computation and say, in terms of energy released, let's state it this way. Energy released by the 1857 tremor, or quake, short for earthquake. We're going to compare that against by dividing energy released by the 1906 tremor. Now at this stage, we just go right to this formula here in the box. or cinnamon roll, however we're doing that. So go to that formula there. We're using the right-hand side. Take the 2.5 times 10 power 4. There is a shortcut to this we're going to mention in a moment. Times 10 to the power of, in the exponent position, 1.5 multiplied by the magnitude. We're putting in the magnitude for the 1857 tremor, and that one was at magnitude 7.9. Then we do it again. We go back to this formula, but we fill in the magnitude for the 1906 earthquake. So we're going to magnitude 7.8. So copy that in again. 2.5 times 10 power 4 times 10 to the power of 1.5 times 7.8. So if you did your due diligence and wrote down the formula verbatim for both numerator and denominator, good on you. That's being really extra careful. But then you'll notice right away, every time that you do this, that's a clean cancellation each and every time. The actual part of the formula that we use whenever we're saying how many times more powerful is one than the other is actually just that. We need the whole formula because some questions in my lab were about one earthquake itself, energy released, for example. But for a comparison of energy, that's what it boils down to. And from here on out, it's all about how you want to put it in your calculator. One school of thought is you can crank out the exponents, take just 1.5 times 7.9, then do it again, 1.5 times 7.8. So those are the two exponents we have in exact form. So it's 10 to the power 11.85, if I recall that correctly. Let me check again. Divide by 10 to the power 11.7. Okay, so all I've done is multiply through on the exponents. At this stage, you can do even more. You could subtract 11.7 from 11.85. If you did that, it would look like this. 10 to the power of 11.5 minus 11.7 is 0.15. So if you went this route, in your calculator, it's going to look like this. Take 10 to the power of 0.15. This wants 4 significant digits. So go to that 4th digit in the line. It's going to round up to a 3, 1.413. So this is one style of computing. I like to go this way because it makes importing the information to your calculator just a little bit easier. If you're not opposed to typing more, you could just go like this. 10 to the power 11.85, divide by 10 to the power 11.7. You get the same exact result. But then again, the more you know about exponent laws, the more insurance you have in the calculator. Just taking 11.85 minus 11.7, getting the exponent of 0.15, makes this way easier to work in the calculator. Either way, we have the same answer. And so that's the total answer to the question, but just for the sake of the context, we can say the 1857 tremor, just to paraphrase once again, was 1.413 times than the 1906 tremor in terms of energy released. But you know, there's really more to the story the more you look into this context. In terms of energy released, joules, sure, the 1857 tremor was worse, but in terms of the size of the catastrophe, how much damage, loss of life that occurred, The San Francisco earthquake was massively, massively worse than the 1857. So it's not always just about the energy released, it's about how much devastation is caused sometimes with earthquakes. That's a little bit harder to measure, but we had a formula for energy in joules. So that's the easier question to answer more exactly. The other part of the story is logarithmic scales are the growth and in terms of what's going on with the magnitudes, whether it's magnitudes of earthquakes, decibels, pH, going from a magnitude of 7.9 versus a 7.8 shows us that a 0.1 increase in magnitude is about a 41.3% increase in energy released, almost 1.5 times as powerful, which is impressive. But that's the complete rundown on this last example. And again, this sample exam that we've done is meant to be a guide of what you should expect on a real filing. We gave lots of hints. Not every single problem in its exact form you should expect on the real exam. Context will change. We made hints along the lines of this one's either half or exponential growth. So there's lots of things like that going on. But this gives you a really great guide on how to prepare. Also, another great strategy for preparing for this final exam is these exams covered, or hang on, your exam 1, 2, and 3 is what I was trying to get at. Your exams 1, 2, and 3 covered a good amount of the entire course. So take another look at your exam 1, 2, and 3. Take a look at your exam that had the lowest grade. That's going to tell you where to focus some of your studying on. Find out what sections those were over, and you can target those sections using either versions of these sample exams that are down here. But looks like we're just about out of time. Any last questions or thoughts, folks, before we call it a night? Okay. Well, good luck with studying for not just this class, but any other classes that you're taking as well. I know final exams week is kind of stressful, but this final exam is not meant to be anything too nasty. If you can get through these kind of problems that you're seeing here, the real final exam is going to be the same about length and difficulty, same style of questions. If you have any questions at all while you're studying for your final exam, I'm going to be available by email as always, so don't hesitate to reach out at any point. I'll be happy to connect with you. But thanks, folks. Have a great rest of the semester as we finalize things. Have a great weekend. Try not to work too hard, and we'll be done with the course before you know it. Take care. Thanks for the kind words as well. Appreciate you all.